Hello everyone, welcome back again to this online structural geology course. We are in our third lecture and today we will learn about structural elements and measurements. So, the topics that we will cover in this lecture are listed here. So, we will first very briefly get very basic ideas on geological contacts and their applications in structural geology. And from that we will switch to attitudes of planar, linear and some angular features that we see in deformed rocks, and then we will ask the questions what to measure and most importantly why. Then we will go to the theory of structural measurements, what the principles behind all sorts of structural measurements, and then we will learn how to measure all these linear and planar features together with how to plot them in the map. So, it is very important that in the field what we see exposed rocks, and you must have understood so far that these rocks, the way they appear to us are extremely puzzling, and this is mostly because the exposures that we see, these are not always continuous. You see some parts here, some parts there and so on. At the same time, it is also difficult to access all these features because they are not preserved everywhere, and these are some sort of characteristics of the field geology which you cannot avoid. So, for large structures, to interpret how it is, what is the disposition and how to interpret the large structures, it is extremely challenging. There is also one point I would like to mention here, that most of the geological observations that we make in the field, particularly in the large scales, are generally two dimensional. Though we see in the field a few meters elevations or few kilometers elevation when you work on active orogenies, but otherwise when we think of the long or large horizontal scale, then the third dimension does not matter. However, it is important that we also interpret the third dimension unless we are working in our 2D models. But third dimension geometry is important because most of the geological deformations do happen in 3 dimensions. And to understand all these deformation features, we have to identify and mark the various geometric elements that we see in rocks. And these elements you can broadly classify in 2 different categories. One is planar and another is linear. To give examples of planar features or planar elements in deformed rocks, you can consider bedding planes, you can consider foliations, schistosity, cleavage, etc., etc. And then on the other side, the linear features are mostly intersection of 2 planes, or we call it intersection lineations, fold axis, mineral lineation, paleocurrent directions, etc., etc. Now, before we go to all these structural elements, planar and linear structural elements, it is important we understand their disposition in the space and time. And there it is very important that you always remember the geological time scale and the stratigraphy of the region you are working with. So, this is important because the establishment of the lithological and stratigraphic sequence is a prerequisite in any large scale structural interpretation and also to unravel the history of the area. It is also important to remember that any structural information, if you do not provide that what is the age, what is the lithological consequences of this, does not make any sense to anyone. So, their age, their lithology, their stratigraphy with respect to the overall geological time scale is essentially important, and these become somehow more complex when we see different kind of stratigraphic contacts. We will see it later what are the different kinds of stratigraphic contacts are, but it is important that there are some sort of normal stratigraphic contacts. That means that you have older layers at the bottom and then slowly you stack up with the new layers. So, if we see this, then there is no problem. However, in the field we commonly also observe an inverted sequence or inverted stratigraphy. That means you have younger layer at the bottom and older layer at the top. Sometimes some layers are missing. That means either they were eroded later or after the deposition, or there was no sedimentation at that particular time. So, if something is missing, then we assign it unconformity. There are different types of unconformities. We are not going into that part. You must have learnt it in your sedimentology or stratigraphy lectures. But if there is unconformity, this is something that we need to consider. There is also a possibility that you see repetition of the stratigraphic sequence. That means a same lithology you encounter when you walk along your field. And all these have very important structural implications and tectonic implications in interpretation of geological structures. So, in nutshell, if I try to summarize what we discussed so far, that why stratigraphic sequences are important, the first thing to remember is that if it is possible, if it is there, try to first figure out what is your primary bedding plane or sedimentary bedding plane. Most of the structurally deformed rocks are metamorphic rocks as well, and it produces many different other layers. We'll learn about it later. But it's important that you learn or you are skilled to distinguish between primary layers and secondary layers. And once you identify the primary layers, then it is important that you try to understand what is the Younging direction. Any deformation structure that we see in the field are essentially younger than the host rocks. That's something that you need to remember, and it's obvious. And if you see that we discussed in the previous slide, any sorts of unconformity in the stratigraphy, inverted stratigraphy, repetition of stratigraphic sequence, etc., all these things, if you encounter in the field, they suggest immediately that there must be either a single or multiple events of structural deformation or tectonic phenomena. So, with this we move to the next part of this lecture, that what to measure in the field. Now, we know that when we deposit rocks, when the sedimentary layers get deposited, then they generally deposit in horizontal manner. So, all layers initially are horizontal, they get lithified, they also stay horizontal. But if you have visited any deformed terrain, you must have seen that these things do not remain horizontal. So, if they do not remain horizontal, that means there must be some sort of deformation in large or small scale. So, in this image we see that these layers are essentially horizontal, and if these are horizontal, there is no problem. These rocks are probably not deformed, or even if they are deformed, they remained as they are. However, you must have seen in the field, or if you go to a deformed terrain, for example in Himalaya, you must have seen that most beds are tilted towards the north side in the Himalaya. For example, this photograph here. Here the beds are not horizontal compared to the previous image. So, these beds are tilted. How to represent that? How to interpret it? That is the challenge, that is the question. So, we have to measure the orientation of these tilted bedding planes. In the second image, we see that a layer is folded. So, in one side of this fold, the orientation, at least in this section, is like this, and in another side is different than the other side of this fold. Now, the question is, can we measure it and can we represent it? It is also important to understand that when these two planes with orientations like this and with orientations like this, when they meet, they produce a line. Two planes, when they intersect, they produce a line, and this line also should have some sort of orientations. And these orientation we will learn later is known as fold axis, and this we can plot as well. So, all these kinds of geometric dispositions of deformed rocks allow us to measure and plot them differently in the map, and this is what we are going to learn now. So, the basics are that, as I said, that there could be points, there could be lines, and there could be planes, and there are many ways you can construct a point, line and planes. But in nutshell, if I have three planes, they intersect, you can generate a point. If I have two planes, they intersect, you generate a line, and then two intersecting or two parallel lines can produce a plane. So, given this background with us, and given the idea that most of the geological maps that we produce are in two dimension, that we produce them in a piece of paper. So, it is important to understand or to plot them such a way that these three dimensional features or three dimensional measurements are represented in the map in two dimension, and this is exactly what we are going to learn now. So, what we measure in the field or the basics of the measurements are considered in general on two planes. One is your horizontal plane, which is represented on the left side, and we call it azimuth. Anything that you measure with respect to the north in degrees on horizontal plane, we call it azimuth. So, clearly you have in terms of degrees 360 divisions from 0 to 360. At 90 degrees you have east, at 180 degrees you have south, at 270 degrees you have west, and there are many in between. Apart from the measurement on the horizontal plane, because we will be talking of the third dimension as well, so there must be something that you are measuring away from this horizontal plane, and this is known as measurement of inclinations. So, inclination measures the angle of tilt or slope at which the plane or line is oriented from the horizontal plane. So, clearly in horizontal plane you measure 360 degrees, but when you measure in vertical it is generally 0 degree to 90 degree and then 90 degree to 0 degree again. But because this is mostly symmetric, so we cover from 0 degree to 90 degree. We will see how these work later. So, based on this background, the structural geologists have their own vocabulary, and these vocabularies considered all these terms. For example, trend, strike, plunge, pitch, back bearing, front bearing, deep angle, and so on. Now, what are these and how to present them in the map, how to measure them in the field is something that we need to learn. So, first, how to measure the orientation of planes or how to represent the orientation of a plane. What we see in this image, that this is an inclined plane, this light brown plate that you see, and if you imagine a horizontal plane is intersecting this inclined plane, then intersection of this inclined plane and the horizontal plane would produce a line. Now, this line is lying on the horizontal plane, and the orientation of this line with respect to the north gives you the azimuth of the strike or the strike of this inclined plane. We will have the definition in the next slide. So, if I have an inclined plane, I know what is the strike of this plane now, and the inclination or the slope of this plane is known as deep angle. Pictorially you can understand that this is the same plane, I just rotated it, and this angle that it makes with the horizontal plane is the deep angle, and the direction this plane slopes is the deep direction. Now, there are some techniques of measuring it. Generally, structural geologists do follow right hand rules, we will learn about it later, but there are many other ways people do measure deep strike and deep directions. I hope the concepts are clear. Let us have the definitions. So, I read what is strike. Strike is direction of the line of intersection between an inclined plane and a horizontal plane. You can also define it, the strike is the compass direction of the horizontal line lying in an inclined plane. If you have the concepts clear from the previous slide, you can understand what these two statements mean. Deep angle is inclination of a plane below the horizontal. So, it essentially ranges from 0 to 90 degrees. You can also define it that the deep is the large angle made by the plane with the horizontal. Deep direction is the compass direction towards which the plane slopes, and if you do not measure your deep angle, perpendicular to the strike line. So, there are many possibilities. These are all apparent dip angles, and the angles along which you are measuring the direction is your apparent dip direction. Let us have a look how to measure the linear features. So, I have the same plane here, and in this plane I have a series of linear features, as you can see. Now, our aim is to measure the orientation or attitude of these linear features. Now, there are three terms associated with these linear features measurements. One is trend, one is plunge, and another is pitch. Let us have the principles behind the measurements. For example, if I take this plane as an inclined plane and I have a series of lines here, then what is trend? So, if I project this line on the horizontal plane, then this back of this pointer is indicating a direction on the horizontal plane. Now, if this is my north, then the angle it makes with along the horizontal plane, this is my trend. The plunge is the angle I have to rotate this line to project it on the horizontal plane, and the pitch is, if this is the line, then if I measure it on the plane, the angle directs the pitch or rec. So, if I try to define it in words, it goes like this: trend is the direction or azimuth of a vertical plane containing the line of interest, or the trend points the direction of a line it plunges. The plunge is the inclination of a line below the horizontal, and pitch is the angle measured on a plane of a specified orientation between one line and a horizontal line. This horizontal line is essentially the strike. Now, from this image we can also realize that trend is azimuth, that is, you measure on the horizontal plane, plunge is inclination that you measure on the vertical plane, and pitch or rec you measure on the plane itself, inclined plane itself you measure the pitch or rec. We will learn more about it later. Now, what is the instrument that you can measure all these attitudes in the field? So, the common weapon or common tool that structural geologists do use are compasses. There are different types of compasses available, but in this course we will mostly look at a very commonly used compass, that is Brunton compass. So, you have the image here, and a Brunton compass, when it is packed or kept its original shape, it's look like this. It weighs about 50 to 100 grams or something like that, and you can open this compass. So, once you open, then you open this lead. So, this part is the lead of the compass. Then you have the fundamental part, the important component, the dial, and then you have one thing that is called sight arm. Now, as you can see, you can rotate it all along from 0 to 180 degrees, same here, and then you can make everything straight as it looks like here. So, we use different orientations of this compass to measure different things, and here in this slide you have the different components written here. Now, what is important, that this is the lead, this is the main dial, and this is the sighting arm. Now, let us have a look what we have inside this dial, because this is most important part that you need to know. So, in this dial we have one needle, and this is a magnetic needle. One end always points towards the north and another end towards the south, does not matter how you orient or how you keep it. Of course, you have to keep it in the horizontal plane. Now, how to make sure that you are keeping your compass along a horizontal plane? To do that, we have one circular, if you look at the slide, we call it bull's eye level. So, keeping this little bubble inside the circle makes sure that your compass is horizontal. So, measurement of azimuths, that is all measurements on the horizontal surface, is assured by keeping this bubble in the center, bullseye bubble. Now, how to make sure that your compass is vertical? To do that, you have another level inside, we call it long level, which is, you can see it is this one, or in the slide it is this one. Now, you can actually rotate this bubble using an arm or lever at the back. So, if I rotate this arm, as you can see here, that this lever rotates, and this lever is known as clinometer, and you can see that this clinometer is graded and also the dial at the back. So, you have to rotate such a way that this long lever's bubble stay at the middle, and that makes sure that your compass is held in vertical manner. So, holding it horizontal or vertical gives you the idea, or gives you the measurements in horizontal, along horizontal planes and along vertical planes respectively. There are some other features, like you have, when you keep it horizontal, this needle generally swings. So, to make quick measurements, you have a little pin here. With this pin, you can freeze this needle when it oscillates extremely less. So, there are some different ways of measuring deep, strike, trend and plunge in the field, but the principles are always same. Different schools have different ways of measuring it. Make sure that while you measure your deep and strike or trend or plunge or pitch, you do it so that you do not damage or you do not break the rocks and rock surfaces. That is the very important message I would like to give you. Do not mark also unnecessarily on the rock surface, like your permanent marker pens and so on. I will upload a separate video on how to measure deep and strike. There are also many YouTube videos. You just search in YouTube and you can find how to measure deep and strike. And while you are doing this, you also make sure that the instructor there is showing you the right hand rule of deep and strike measurement. Here are the instructions. I am not going into the details of it, because I will upload a separate video that you will click and see it later. But few things you have to make sure that your compass is essentially horizontal when you are making strike. When you are measuring deep, it is also important you make sure that here in this lead, in this long lead, your bubble is right at the middle of this lead, otherwise you will not get the actual or true deep. Okay? Now, how to note deep and strike in your field book? That means you measure in the field, fine, but you have to note it so that you can reproduce it in the map or later use it for analyzing data, because in the field you measure 100, 200 and so on deep and strike data. Interestingly, there are many styles. Structural geologists used to note deep and strike, and sometimes they are confusing. So, I am giving you what are the general ways people try to write. The usual convention that people follow: first you write strike, then you write deep angle, and then you write deep direction. But if you follow this right hand rule of measuring strike, then you do not have to mention deep direction. You just have to add 90 degrees with your strike, and then you get your deep direction. There is also very important convention that you have to remember when you write strike or anything you are measuring on the horizontal plane. That means any azimuth you have to write using 3 digits. So, if your strike is 78 degrees, just do not write 78, write 078. So, it must be in 3 digits. Now, how to note it? So, what example I have given here, that if you have a plane with a strike 120 degrees that you measured following the right hand rule, and dip angle is 45 degrees. That means the strike line is 120 degree and the plane is dipping 45 degrees. So there are three ways you can measure, you can note it. First one is just 120/45. This is if you use your right hand rule. You can also write 120 degree, 45 and then an arrow 210, that is the direction it is sloping. That means it is sloping towards southwest. So you can also write it 120 degree /45 southwest. So a 3-digit / 2-digit format. Now this is how you note in the field notebook your dip and strike and dip direction data. But how to plot them in the map, or how to read them in the map? If you are looking at a structural geology map or a structural map, you will see many symbols. Now you have to understand what is what. So if you have a normal dipping bed with the same orientation 120 degree 45 degree, then the symbol is something like that. You have a longer line that dictates or that indicates the strike line. So it is generally drawn, or it is generally mentioned with respect to the north of the map, and then perpendicular to this giving the direction, it gives you the value of the dip and dip angle and also the dip direction. If the bed is overturned, then the symbol is like this. If the bed is horizontal, then the symbol is like this, and if the bed is vertical, then it is given like this, where the strike is given with a longer line. So there the plunge you also measure in a similar way. I am sorry, it is not the similar way, in a different way, but it is done with the same compass and it is done differently, but the technique or measurement principles is always same. How you do it, it is written here, but as I said, I will upload a separate video on the measurement of trend, plunge and pitch of a linear feature in the rock surface. Okay, so we will now look at how to note or write in your notebook trend and plunge, and also we will see how we should plot this trend and plunge in the map. Now interestingly, unlike dip and strike, where geologists do write dip and strike in different ways, but for trend and plunge there is more or less a very unique style, and the unique style is first we write plunge and then we write trend. And the same rule applies here. That means if you have to write strike, then you have to always write in 3 digits. That means if your trend direction is 78 degrees, you do not write it as just 78, you write it as 078. This is simply because trend is measured on the horizontal plane, this is azimuth, so it is better you write this in 3 digits. And if we assume a linear element that has a trend of 080 degrees and it is plunging 56 degrees, that means it plunges 56 degrees towards 080 degrees, then you can write it 2 different ways in your notebook after measurement in the field, 56/080 or 56 indicating an arrow towards 080. Now both of them have more or less similar meaning. The first two digits, this indicates your plunge value, and then next 3 digits indicate your trend value. Now in the map again it is the trend because it is measured on horizontal plane. So given the north of this map is in this direction, then you draw a line, and then this line would indicate your trend. And if the plunging is happening on 56 degrees, then you actually mark this 80 degree towards this side, and then you mark the 56 degrees. I repeat that you draw a line and then the plunge, if it is directing towards 80 degrees, then you mark an arrow towards that side, not in this side, but in this side, because this is the direction your plane is sloping or plunging, or you not plane, sorry, your line is sloping or plunging, and it is 56 degrees. So, this is how you write. If it was, say, for example, 0 degrees is your trend and 40 degrees your plunge, then with respect to this is your north, then you would make it like this. So, that indicates 0 degree and 40 degrees plunge. So, you write it like this. Once you have all these data measured, here I show you a very classic example of how to plot these data and represent them in the field. So, on the left side you have a Google Earth image showing the two classic synforms that we see, and of course, one antiform in between in Shingbum area. So, these two synforms, this one and this one, are on Dolma volcanics. You have classic Shingbum shear zone here, the river Subarnarekha is flowing in between, and the entire range is known as Chaibasa formation. You have this classic place Ghatshila located somewhere here. Now, once we see this and you would like to represent it structurally, the one of the classical maps I like of this region is made in 1962 by Sarkar, and this is how it is. You can download this paper and look at this map. But in general, our students also do plain paper mapping where you do not have any help of the topography. So, this is one of the maps our students produced in the field, and all symbols here are different measurements of planar and linear data, and this is how a map can be produced. So, with this note I conclude this lecture. In the next lecture we will learn how to analyze all these structural data. You cannot plot all your data in the map, and even if you can plot, it is important that you summarize them, you interpret your structural data, and to do that we use a technique called stereographic projection. That will be a topic of the next lecture. So, thank you for now and see you in the next lecture. Bye.